So I coordinated with Chris, who just gave the introduction to the quantum random oracle model. So what I will do in this last hour of the day is I will give a little bit more detail about this compressed oracle technique, which is basically, I think I can say, which is the most powerful technique we have to prove security in the quantum random oracle model. And I want to do this while letting myself be guided by the idea of extractability via random oracles. So here's an outline. And I want to start with taking another look at the compressed oracle. So here's Chris's slide about the compressed oracle technique. And the main point was that through the magic of quantum computing and the Fourier transform, we can kind of change the basis of our oracle unitary in a way that instead of having the oracle write information into the query algorithms register, we all of a sudden have the oracle write information that is read from the query algorithms register into the oracle register. So this was really a crucial insight, and it allows us to do many things. So one thing that that kind of also follows from this idea, if you look at the right side here, is that after the fact, you can see that if x was 0, then the eta is in the 0 register, or in this first, in the f of 0 register, let's say. And if x was 1, then it's in the f of 1 register. So one thing that one can realize is that while I have no idea what this algorithm did that made some queries, I can see by looking at the oracle registers, I can see whether 0 or 1 was queried by the algorithm, right? But because I can see which register is still in the 0 state in the Fourier basis and which one is not in the 0 state. However, there's much more information there, right? I mean, I can actually see this eta value, which is the Fourier basis state. So I can see with which Fourier basis state the algorithm has made this query. That's, however, not actually very useful information. So actually the only thing I care about is whether it's 0 or non-zero. And other than this bit of information, I'm actually interested in the standard basis, because in the standard basis, that's where the actual function values are stored. So let's just try to recapitulate the purpose of this Fourier representation of the oracle. So first of all, one purpose was this idea of compression, so that instead of having this exponentially large function table, we can store a sparse representation of it, because in the Fourier basis, most of these function table registers are just in the 0 state. So instead of storing these exponentially many, having these exponentially many registers around, where most of them are 0, I can just try to store pairs of values where I have the index of the register, or let's say the input of the function where this value corresponds to, and the corresponding Fourier function value, or Fourier basis state. So that's the idea of compression via a sparse representation. And as I just said, like one thing that's very useful is that we can basically do this, what I sometimes like to call oracle forensics. So after an algorithm has interacted with this compressed oracle and has finished, we can inspect the database to see what values did this algorithm actually query, or what outputs of the function does the algorithm have information about now. So we can kind of revisit this idea and try to, sorry, one more thing I wanted to say is actually what you want to say is, what you want to know is, was X queried or not? And if so, what value does the function have at this input? So let's kind of revisit this and try to make only the minimal basis change that facilitates the achievement of these three purposes. So the idea is now to, instead of just taking the Fourier transform, to just do kind of the maybe the most natural thing if you think about the sparse representation. So in the sparse representation, if you have a sparse representation of vector, you have a default symbol, for example 0, and then you only store the non-zero values. So now I'm just, one could just think about introducing a new default symbol that's separate from all existing basis states of this register, and only basically map the initial state of the register to this default symbol and leave everything else as is. So let's try this. So here's the first attempt. Basically, let's try to, let's now think about a register that has 2 to the n plus 1 basis states. So it has the 1 basis state for each n-bit string, but then in addition it has this bottom symbol basis state that's kind of an additional dimension of this vector space. And now I want to define a basis change operator, so that's a unitary operator that maps our initial state that I denote by plus to the n, because it's just the uniform superposition. I can think of this as the n-fold tensor product of the plus state. That maps that to my special default symbol bot, and for any standard basis state, I would like to preserve that, right? I mean, I want that basically, if I apply it to x, then it maps to x. Does anybody see a problem with that?
It's not uniform.
It's not unitary, that's right. So that's too much to ask, because I'm trying to specify this unitary operator, and I'm specifying arbitrarily here what it should do on non-orthogonal states, and that's not okay. Like I cannot, in general, find such a unitary operator, and in this case, yeah, I cannot find such an operator. So that's no good. Instead, let's do the next best thing, which is basically to say that, okay, if we still want to map the initial state of the vanilla superposition oracle to this bottom symbol. So, by the way, this is just specifying what happens to a single register in the database. So this register is supposed to store a single output of the function, let's say at the input 0, for example. So I still want that the initial state, the uniform superposition, is mapped to this bottom symbol. And now I kind of complete this in the minimal way possible. So I just say, just for completeness, I also map the bottom symbol to the initial state under this basis change unitary, and I introduce the bottom symbol as an additional orthogonal basis direction, so that's fine. And for now I want to say everything else I leave as is, and the way I need to specify this is I need to say any state that is orthogonal to whatever I've already done, or wherever I've already defined the unitary, I leave untouched. So basically, for every phi that's orthogonal to the bottom state and to the uniform superposition state, I define V to preserve that state phi. So now I have actually specified a unitary operator on an orthonormal basis. And so this totally exists. I can apply it and everything. So that's nice. Now, basically what that means is we have a new defined kind of a new variant of this oracle. Like we already had the standard oracle and this Fourier basis oracle. So instead we now have an oracle that has a new database register where each function value register is augmented by this one additional state that I denote by bot. And the initial state of this oracle is just the state where all the registers are in this bot state. And now compression is very easy. If some algorithm makes a number of queries to this, after q many queries, it turns out that only q many of these registers are not in the bottom state in superposition. So I can perform the same sparse representation type compression that was possible in the Fourier basis. By the way, interrupt at any point to ask questions. I mean, I think we have already established this culture now at this school, so please go ahead. So let me call this oracle the pre-compressed oracle, because what I want to do is I want to keep the exponentially large function table for convenience of manipulating this, because actually it turns out that the efficient representation, the sparse representation, is kind of cumbersome to deal with if you want to define the oracle unitary, etc., etc. So I want to keep the exponentially large internal register of this oracle, but I apply this basis change so that I have this additional bot symbol, and the initial state of the oracle is the all bottom state. And so, in general, I have the situation where some algorithm can possibly get some input alpha. It now interacts with this oracle simulation. It expects a random oracle, but we can now simulate this random oracle with our pre-compressed oracle. So it makes a number of quantum queries to this pre-compressed oracle, and in the end, it produces some output beta. Now, the good thing is, in the end, after it has the algorithm has finished, we don't need the database anymore. So we can think of the pre-compressed oracle basically outputting it, right? And in particular, we can just perform a measurement of the entire database. So what does that give us? That gives us this collection of values yx, one for each string x, because basically it's a measurement of this augmented function table. And each of these yx can be either an n-bit string or the bottom symbol. Now, can we interpret what this yx means? So the idea is the following. The idea is we would like to have the following interpretation. So if yx for a particular x is equal to bot, then the algorithm A has not learned any information about f of x, right? If we think of this pre-compressed oracle simulating a random oracle f, then the algorithm has not learned this function output. However, if yx is equal to y, which is some n-bit string, then we want to interpret this as the algorithm has queried x and f of x is equal to y. Now, if you remember, we weren't able to actually preserve the content of this database register exactly. So actually, maybe the best we can ask for is that this second point here, this second bullet, holds except with a negligible probability. Does that make sense? So basically, the idea is now we have this oracle simulation. It's indistinguishable from an actual quantum accessible random oracle. but with the added benefit that in the end we can measure the internal database of the stateful oracle simulation algorithm and get all this information about what the algorithm has learned about the function that was simulated by this oracle. So now let's just for a second contemplate yes?
Sorry, just a question. Can you maybe just explain again what I missed is, so when we construct this database, how big is it, or like this, can we do this efficiently? Like I wasn't sure.
So I kind of
okay.
What I can say is it's possible to simulate it efficiently, but for this talk and also for any proof where you don't need the efficiency, it's so much more convenient to work with the inefficient version, where essentially you have this database that has 2 to the n many registers. Each of them has a little more than n qubits, basically n qubits plus 1 extra dimension to store this default symbol. So that's this exponentially large database that we're talking about.
Okay, thank you.
Any other questions at this point? Okay. So let's just contemplate for a second how surprising this actually is. I mean, you know, we have this algorithm. It makes quantum queries to a random oracle, or that's at least the initial situation that we're thinking about. And note that there is this thing called the null cloning theorem that Julia also mentioned this morning, which says that you cannot make a copy of an arbitrary, and in particular not of an unknown quantum state. So if we think about proving a reduction, for example, we cannot take an algorithm that makes quantum queries to a random oracle, for example, and, you know, make copies of each query to compile what's called a query transcript or a list of queries. That's like a priori not possible, but it turns out that there exists this pre-compressed oracle, which is a stateful simulation of a random oracle that achieves almost that, right? At least if what I just showed you in this red box, the interpretation is actually accurate. I have not proven that to you yet. So that's kind of very surprising and extremely useful. Maybe I can give a little example to illustrate how useful it is just on a high level. So suppose I think of the situation of the one-way to hiding lemma, right? Chris showed this example of an encryption scheme where basically things went wrong whenever the algorithm queried a particular input. Now I can, you know, after the fact just check, you know, is the corresponding yx actually bottom? If yes, then the algorithm has not queried that input. You know, conditional on this interpretation. Okay, so I think something went wrong with the overlays here. I am sorry. Now I want to make this interpretation more formal. There's this thing that I like to call the fundamental lemma of the compressed oracle technique, and it reads as follows. So if we have some quantum algorithm A and some relation R, and this A that has a quantum query access to a random function f, then we can compare 2 experiments. One of them is kind of the defining experiment that kind of defines this type of situation. A gets an input alpha, it makes quantum queries to the function f, and in the end it outputs, it produces an output. And in this case, I think of the output as being a pair xy. Now, I can think of an alternative experiment where I replace the random oracle for the function f by this stateful oracle simulation that I call the pre-compressed oracle. And after the algorithm has finished, and output its pair xy. I consider the database register D of this compressed oracle as an additional output. I measure it and produce these yx. Now, the actual statement is now a statement that compares these two experiments. And it's as follows. The probability that for that output xy that the adversary produces in experiment 1, that y is actually equal to the output of the function under the input x, and the pair x and y is in relation, in the relation R, that can be upper bounded by kind of a similar probability, where instead of the function value at input x, I consider this string yx that I measured from the database, and still I want that the pair is in the relation. And this holds up to a tiny error, to the minus n-half. Yes?
Sorry, it's a very naive question. I didn't understand the significance of the relation R. I mean, we're already checking that y is equal to f of x for, some function f, right? So why do I need to additionally have this relation R?
So I think, okay, I might be mistaken, but I think I think this is a more general statement if I add this relation R. And for example, suppose I want to prove that in these two situations, the probability that A outputs a pre-image of 0 is equal up to a small error. Then I want that xy is an input-output pair of the function, but also I want y to be 0, and I need to be able to put this condition into the probability expression. And the most general way of doing this is via relation R.
But I mean, if the output is 0, then it's not a random output.
Yeah, but note that the adversary has chosen this the input-output pair. So it might have, for example, Grover search for an input that maps to 0.
Okay, thanks.
Yes. Yeah, the question was what the probability is taken over, and the probability here is taken over everything that's random, and in the experiment I, that's the probability, that's the randomness of the random function f, and the randomness of any measurement that the algorithm A has performed to produce its output. And in the experiment II, or in the experiment 2, it's taken over the probability of all measurements, which here is the measurement that measures the database D, and the measurement that the algorithm makes to produce its output.
This might be a bit of a general question. What type of computational assumptions are you making on the oracle? Like what type of power does it have? What
computation assumption I make on the oracle or on the algorithm?
Both.
So the algorithm is arbitrary. The only assumption I make here, I mean, basically the algorithm is arbitrary. The good thing is I can compare the same algorithm in these two situations. And for example, if I have a bound on the number of queries that it makes under any oracle, then this bound will hold on both sides.
Okay.
And the oracle it's a concrete algorithm, right? It's an interactive quantum algorithm that statefully simulates some oracle, and it has a concrete runtime. So in fact, if I think about the efficient simulation of it, it runs in time order. It's polynomial in the input-output and output lengths of the function and the number of queries.
One small question about the database. These outputs that we get there, these yx. So we know so for every yx we know what the x is in this representation. So we know what x corresponds to. So my question is basically, could you have also written it as pairs like x and yx, and would still be correct, or?
Yeah, that's still correct.
So
I mean,
we know which x this corresponds to. Okay, but these y's don't have to match the y's in the real random oracle world, and yeah, that's the difference.
Here I just think of an ordered list, right? It starts with y that corresponds to the all zero input, and then etc. up to the y that corresponds to all one. Okay, so let's continue. Now we want to make good use of this lemma. And what I want to revisit now is how to get query complexity results from the compressed oracle. Because we will use this later to prove that certain extractors work in the quantum random oracle model. So here's Chris's slide again. There's this theorem that says for any quantum player making Q queries, if the database D is measured after Q queries, the probability that it contains a pair x, 0 to the n is at most order Q to the n divided by 2 to the n. And this you can, now that we have seen this fundamental lemma, this is basically a way to make a rigorous connection between the database containing this pair and the probability that any adversary can actually output such a pair. Because this was kind of maybe swept a little bit under the rug in this in this high-level idea that we still need to connect whatever happens in the database rigorously to what the adversary can output. So basically, if you take this theorem and together with the fundamental lemma, we get a theorem that up to this small error that's independent of Q, this bound also holds for the probability that any adversary can output a pair x, 0 to the n, where such that f of x is equal to 0 to the n. And I want to now look a bit closer at this. And in particular, there's this last remark here that we're using newer tools from this work by Chung, Fair, Huang, and Liao, that one can kind of convert this kind of proof into a classical reasoning. I don't want to explain this part where they build up a framework that one can use classical reasoning to prove quantum query complexity results, but I want to take their point of view on proving query complexity results from the compressed oracle to explain a bit how that works. So here I have a picture of a query algorithm A. It has, in this setting, it interacts with this pre-compressed oracle. So there are 4 registers. The register D is the internal register of the pre-compressed oracle. The registers X and Y are the query registers that the adversary, periodically submits to the oracle to get the oracle unitary applied, and then it has an additional register E, which is an internal working register of this algorithm. And it makes Q queries, as you can see. Now, what we would like to characterize is the following. So I just take the same unitary part of this algorithm. What I kind of omitted here is any final measurement that the algorithm might make. But what you want to kind of quantify is the hardness of converting a database register D where some property P does not hold, and here we kind of indicate this by this box that says not P, and we can think of this as a projector. So it projects onto all databases that do not fulfill the property P. And then we want to quantify the hardness of converting this database that does not fulfill the property P into a database that fulfills the property P. And that's indicated here by the box with P. Now, in the example where we are just trying to find a preimage of the 0 to the n output, as said, it's possible to prove that in some sense this expression, and I'm being hand-wavy here, is smaller or equal than c times q divided by 2 to the n half. And I want to be more precise now. So let's copy this. And what we actually mean is that the operator norm of this linear operator that results from applying the initial projector, running the unitary, like applying the unitary that represents the quantum algorithm, and then applying the final projector, that the operator norm of this linear operator is bounded by this expression. And I want to now basically give a proof in pictures of that. Or at least a part of a proof. So first of all, we can omit this final unitary here, because it's a unitary operator. It doesn't change the norm, and in particular also it doesn't change the operator norm. So we can omit it. Let's move this final oracle over here, and now I insert a small identity operator here. Of course, applying the identity doesn't change anything, so I put one here. Now I express this identity as the projector onto basically the OR of these two things. Either the database fulfills the property or not. And of course, one of the two needs to be the case. So if I project onto any of these two cases, that's the identity. And now I can write this identity as the sum of these two projectors. So let me explicitly do that. Now I have a linear operator that consists of one run of this algorithm where I have inserted the projector P right before the last query, and one run of this algorithm where I have inserted the projector not P right before the last query. And now the remainder is basically just a little bit of, let's say, linear algebra mumbo jumbo. So I apply the triangle inequality. I have the sum of two operators, and the norm of the sum of two operators is smaller or equal than the norm of the sum of norms. Now these are projectors, so I can actually double this projector. P squared is equal to P for any projector P, so I just, make it 2 copies. And now I apply something called the submultiplicativity of the operator norm. So the norm of the product of two operators is smaller or equal than the product of the norms. And now I want to say that basically the operator in the upper right corner, that's not very small, because basically it's just the probability that the database fulfilled, the maximum probability that the database fulfills some property, and it still fulfills it after another query. And similarly in the bottom left, where it's the same with the property not P. So at least that's not very hard to achieve. I can maybe just even make some queries where I forget the output again or something, and then I don't change the database. So I'm upper bounding these terms by 1. And now I have this expression that says that basically if I started with a Q-query algorithm, I've reduced the problem to a Q-1 query algorithm in the top left. And this very simple expression where that says basically the operator norm of one query to this compressed oracle, converting a database that did not fulfill the property to a database that fulfills the property. And now the only thing we need to do is we need to induct, and then we get this inequality that says that the initial operator norm that we were trying to bound is bounded by Q times this simpler operator norm. And the last step now that I will not show how to do is to bound this simple expression for the particular property we're looking at. And it turns out that in the case where we're looking at the property that the database contains some preimage of 0, we can bound this operator norm by 2 to the n half, 2 to the minus n half. This was the end of the basically this partial proof of this kind of query complexity, general query complexity results. So maybe this is a good point to quickly pause and see whether there's any questions.
Just very briefly, if you go back to the original expression you wanted to show, what was the bound you had, the formula, like at the beginning of this proof that you wanted to show? I just want to see it again. So this one, yeah.
Yes. So there's q times 2 to the minus n half, and the way we show it is we first reduce to the simple expression, but q times, and then the part that I didn't show is that the simple expression, the probability, the maximum probability that the one single query converts a database that doesn't contain a preimage of 0 to a database that contains a preimage of 0 is 2 to the minus n half.
And this capital C just comes from these things that you bounded by 1 and these kind of, where does C come from?
I mean, it's a constant, and basically, you know, if you look at Chris's slide, he had a big O. So I didn't question this further, so I just put a constant.
Oh, okay. When you
but I think there's even like if you use the framework by this framework by Chung, Fair, Huang, and Liao, there will be a constant. I think it's maybe 10 or something like that.
Okay, thank you.
So now I just wanted to give a short overview of what one can do with this kind of stuff, with this kind of reasoning, right? So first of all, it's you can prove query complexity bounds. So one can prove the hardness of preimage finding or collision finding. These were actually known results that were reproven. There are other techniques in quantum query complexity one can use to prove these bounds. However, there are also new results that were proven, new query complexity results that were proven with this technique. For example, the tight complexity bounds for finding several collisions or several multi-collisions or multi-collisions was proven with this technique. And also it's a bit more general. One can, for example, use this framework to analyze proofs of sequential work, or give space-time trade-off for query complexity function problems. And one can even use it to analyze non-interactive zero-knowledge proofs of certain types. Okay, now I'm ready to move on to the I guess the main part of this talk. Let me quickly have a look at the time, and that's about extractable commitments in the QROM. So first of all, quickly, let's recap what a commitment scheme is. So Alice has a message M, a message here depicted by this envelope, and basically the commitment scheme is a cryptographic analog of the following situation. She puts this message into a safe and sends the safe to Bob. Now, some time goes by, and if eventually she wants Bob to have the message, she can send Bob the key to the safe, and Bob can open the safe to retrieve the envelope. Now, we want such a scheme to fulfill two things. First of all, Bob should not be able to learn the message before receiving the key, which is called the opening. And also, in addition, this commitment should be binding in the sense that Alice cannot, I mean, in this physical example, that's obvious, Alice cannot change the content of the envelope while it's already in the safe and at Bob's location. So cryptographically, one easy way to implement such a functionality is using hash functions. So how does that work? Given a message M that Alice wants to commit to, she samples some random string R, and then she hashes the message M concatenated with the random string R. to obtain the commitment C. And then she sends the commitment C to Bob. Now, after some time, she might want to open this commitment, and the only thing she needs to do is just send the message and the random string. And Bob can now check, does this pair actually hash to C? If so, then this is a valid opening, and he has also learned the message M. Does it have these two properties? Yes, it does, because hiding basically follows from the fact that just given C, to find M, one would basically need to find a preimage of this hash function, and that's something hard. That's a guarantee by the hash function. And in terms of binding, basically to change, if Alice wanted to change her mind about the message M, she would need to find another message M prime, and another randomness R prime that hash to the same value, C. And that's hard by the collision resistance of the hash function H. Now, all of what I've said until now is easily possible with a standard model hash function. That's basically a hash function family that is collision resistant and preimage resistant. However, I can get something extra if I am moving to the random oracle model, and that is what's called extractable commitments. So here I have the same scheme, except that now I model the hash function H as a random oracle that Alice needs to query to produce the commitment. Now, what's possible now is basically to just take the commitment C and to extract the underlying message M. So that's at least the idea. So I have this extractor algorithm, and I wanted to take the commitment C and extract the message M, and it should be efficient. So does anybody see a problem with that? Just checking whether everybody's awake still. Right, at least as I draw it here, this is an algorithm. It just takes the commitment C as an input, and it should output the message M in the end. That should not be possible by hiding. So what I need to do is I need to give the extractor some kind of superpower. And the superpower is that I give the extractor another input, which is the list of queries that Alice has made in the process of producing this commitment. And now, basically, this is fine, because now I have an easy algorithm. I will just look through this list and find one of the queries where x is equal to some value m and r, and h of x is equal to c. And I output m. So why does this work? So now we have to think of a malicious Alice that produces this commitment in some weird way. But we still want to think about her being able to open it, right? So if she's able to open it, she either needs to make a query to produce this commitment C, or she needs to, after the fact, find a preimage of C. But that's hard. So basically, because of hiding, if M is not in Alice's query list, then she cannot open, being an efficient algorithm. And as an added benefit, because of collision resistance, because of the bindingness of the commitment, I know that the extracted commitment will be the same, the extracted message will be the same message that Alice later might be opening. So that's great. Now I have this extremely simple construction. I didn't even put an attribution. I'm not 100% sure who first came up with this idea. Maybe Pass. But it's a very simple idea using basically shifting all the hardness of this type of functionality into the magic of the random oracle. So now let's do extractable commitments in the QROM, in the quantum random oracle model. So we have the same scheme, right? And everything is still classical, right? Because if Alice is an honest algorithm, the only thing she needs to do is she needs to make a classical query to the random oracle to produce the commitment C. However, if we're thinking of a malicious committer, we need to give them quantum access to the random oracle if we want to have post-quantum security of this commitment scheme. So now let's see whether our extraction strategy still works. Well, do we have a list of queries? Not really, right? At least we cannot just make copies of the queries, as I earlier pointed out. But the good thing is, instead, we can basically, we can use the pre-compressed oracle. So now, instead of, we give the extractor algorithm the ability to provide any oracle to Alice that they please, right? So this pre-compressed oracle, it has an internal database D, and if we now have our extractor algorithm again, the new superpower we will give to this algorithm is the ability to make measurements on the database D. So what is the extractor algorithm? It just measures the database D to obtain something. Earlier I called this list the y-axis for all string x, and now by analogy, I just call it L. So I measure the entire database D in the computational basis to obtain a list L, and then I just find a query where x is equal to some MR, such that the output value, so the y-x, is equal to C. And I output M. I forgot to put that on the slide. So now the question is, why does it work, right? That's kind of, now I put this kind of in this faint color, because the same argument as before, it kind of doesn't work, right? I cannot, I would like to say that if M is not in L, then Alice can't open. But at this point, before Alice was even computing her opening, I made a measurement on this database. So I might have destroyed it. I might have changed this pre-compressed oracle in a way that makes it not actually an honest simulation of a random oracle anymore. Was it to be used after that measurement? And also, the second part is maybe not immediately clear. The uniqueness of the extracted message. However, that's kind of okay, right? Because we already have the query complexity of finding collisions in the pre-compressed oracle via, for example, this framework by Chung, Fer, Huang, and Liao. So we can still prove that the extracted M is unique. So there will only be one query that has output C, except with negligible probability, as long as Alice is efficient. So how about the first part? That part is a bit more difficult, and I want to describe now why. The problem is basically that we need to make a counterfactual argument. So kind of once the commitment is output, we have two ways to continue our experiment. Either we continue to let Alice do her thing, and eventually she produces an opening of the commitment. Or we can apply the extractor to extract the message M. But we cannot, they don't exist in the same probability space, because if I run the extractor, then kind of that extractor a priori speaking just destroys the compressed oracle, and I cannot continue to run Alice. So let's make this a bit more precise by again depicting Alice's algorithm. Now Alice is this algorithm A here, and I think of this as kind of an interactive quantum algorithm in the sense that it runs for a bit, then it makes a measurement to produce the commitment C, and then afterwards, maybe after some time, it begins to run a little bit more, and then eventually it outputs this opening M, R. Now, here is the additional measurement that produces the query list L, and as I said, like in general, that invalidates the rest of the algorithm. We changed the algorithm, that's why I kind of call it A0 prime, and we don't know anything anymore what it's going to output in the end. What we would like to say basically is, because A could have opened the commitment, L will let the extractor extract M. The missing ingredient for this, at least for the purpose of this talk, is what's called the pinching lemma. So let's read it together. We have some quantum algorithm and an X prime, which is just a bit string. So now we define a modified quantum algorithm A0 that basically runs A, pauses somewhere in the middle, makes a measurement, but this is a measurement that doesn't measure the entire internal state. It just makes a partial measurement that produces one out of k possible outcomes. And then it resumes A and runs it until the end. Then for any possible particular fixed output X prime, basically the probability that the algorithm A outputs that X prime, it cannot decrease too much by making this internal, this kind of intermediate measurement. So basically, while we have possibly significantly derailed the plans of this algorithm A by making the measurement in between, which collapses the state as Giulio described this morning, the probability of producing a particular output X prime doesn't decrease by more than a factor 1 over the number of possible measurement outcomes. So that's great, right? Because if we think about our situation again, now, you know, I said that we were going to measure, make this huge measurement that produces the entire database L, or this entire query list L, but maybe let's make a more, maybe a less invasive measurement that just measures the bit. Does there exist a register where the output is C? So I can kind of formalize this. We can think of this as like some quantum algorithm that computes this bit in superposition, and then we measure the output, and then we uncompute the quantum algorithm. So basically, there exists some measurement that only has 2 possible outcomes, and that we can make to determine whether our extractor would have succeeded or not. And then we continue to run Alice's algorithm and let her output her opening. And now by this pinching lemma, the probability that the output, the opening is correct, it doesn't decrease too much. It's still larger or equal than the probability that the opening is correct in the plain run of the experiment divided by 2, because we applied a 2 outcome measurement. Now, the good thing is, we know that by the technique of, by the query complexity technique, that transforming a database that does not fulfill a certain property into a database that fulfills a certain property, that can be hard. And in particular here, we're talking about transforming a database that does not fulfill the property that there exists a preimage of C into one where there exists a preimage of C. And that's hard. We can quantify this by, again, bounding it by Q squared over 2 to the n. But now the number of queries is basically just in the second phase of Alice, because we're thinking about the bit B equal to be 0, so basically there not being a preimage of C in the intermediate measurement. But then after Alice runs, if she still outputs a good opening, there must have existed a preimage at that point. So basically, by concatenating these two inequalities and adding the probability that the bit was actually 1 and the extractor succeeds, we get a bound that relates the success probability of the extractor, here the probability of B equal 1, to the probability that Alice was able to open the commitment. So this is a good point to pause for a second. Maybe there are some questions.
Just a small question, but it's going a bit back when we were still in the classical case, like classical random oracle for the extractability. So now we are kind of programming the random oracle. So in the QROM, the extractor can kind of program or can control the random oracle. So could we have, in a classical case, could we have even simplified the proof and just say the extractor already doesn't get this list, but he just runs, so he simulates the random oracle to the adversary, and then he knows, or I'm just trying to figure out
that's
the
basically
difference between these two views, whether I get this list as the extractor, whether I'm actually allowed to play the role of the oracle.
So that would have been an alternative in the classical setting. It's just not necessary. In this case, the best thing that the adversary, the extractor could do is sample, simulate the oracle honestly, and then read off the query list. Good. So basically here's a theorem, but maybe in the interest of time I will just not read it. But what it says is basically that this extraction works if L is outputted in a valid opening. So actually kind of the technique that I showed you is I kind of came up with it for this talk because there's another technique that's a bit more complicated that that I wanted to avoid describing. And so with this other technique, the factor of 2 is not present. And in fact, we can prove that even if we make a measurement that actually extracts the message, then Alice's algorithm is still not properly disturbed, and she will still be able to output an opening up to a small additive loss. And this uses reasoning via the norm of commutators. So that's a particular expression from linear algebra. So what can we use this for? These type of extractable commitments. Turns out that we can prove straight line extraction results, so proof of knowledge property for certain Sigma protocols, so certain interactive proof systems, and it can also be applied to the Fujisaki-Okamoto transform. So now the next part, the last part would have been applications, but I guess I'm 1 minute over time, so I should probably postpone this to you reading the slides. Thanks.
Thank you very much. Do we have any questions to Christian? Yes.
So in the extractable commitment application that you showed, we were giving the extractor a certain superpower, right? And a lot of the hurdles that we faced were specific to the superpower we were giving, like basically this thing that you will measure the database, right? Can there be other meaningful superpowers that we give? I mean, I see that this is a natural one in the quantum setting, like to sort of mimic what happens in the classical setting. But do you think there could be other ways of empowering the extractor that would not run into these problems?
I guess there's definitely other means. So, for example, I mean, classically, maybe the most well-known alternative is rewinding.
Yeah.
And so for that, one needs to make the commitment interactive. But that's anyway necessary to get extractable commitments in the plane model. And rewinding has its own sets of challenges in the quantum setting, because basically I want to run an algorithm, measure the output, and then rewind, but I've already measured, so in general I have changed the state. I cannot go back to a particular point in the past. There's also, at least the the theoretical possibility to just stop the algorithm at some intermediate query and measure the query. That's basically what the one-way to hiding lemma does. That's a very invasive thing. It will create even more problems, usually.
Okay, thanks.
So, yes, we have one more question.
Yeah. That was the case where... So, in one of the last slides, there was a case where we only extracted the 1 bit of information, and then we only had to divide by 2, and I think I just keep the motivation for this, and why this is satisfactory for us.
Yeah, so basically, yeah, maybe I just didn't describe this in enough detail. So the idea is, I have this tool that lets me kind of bound the loss and success probability if I make a measurement that only has few possible outcomes. But what do I actually care about? I actually just care about whether the extractor succeeds or not. So the actual output of the extractor, maybe producing the actual output of the extractor is something that actually prohibits Alice from continuing and producing her opening. But I want to kind of, I want to be able to apply the query complexities result that says, if my extractor would not have succeeded, then producing an opening is hard. And to basically use the success probability in the undisturbed experiment for that reasoning, I make the minimal measurement, which just measures the bit of information, would the extractor succeed or not, were it be allowed to run.